All right, guys, we're going to do a short lesson today. I know you're focused on your test for tomorrow. No big deal on these linear inequalities. I want to just, we mentioned these in class. If you're fully remote or you were absent Tuesday, just a quick peek into what's coming up next week. We are not going to spend time on this at all. 2 days, we're going to move along. Linear inequalities, we want to harken back to, that's a word, right? Harken back to when we did these inequalities in one variable. And we looked at things like x is less than 3. And you remember what we did with these on the number line. There's a 3. That was an open circle, arrow that way. Or x is greater than or equal to negative 4. We found negative 4. That was a closed circle with an arrow this way. So that arrow represented all of the numbers that are less than 3, or all of the numbers that are greater than or equal to negative 4. My dog is here thinking on my bed with me, thinking that I'm teaching him about inequalities. The reason we have the arrow is we can't possibly list all of the values that are less than 3, so we graphically represent them instead. Well, now we'll look at linear inequalities in two variables. So we want to look for xy combinations for this example so that the y value is less than the x plus 1. Well, let's see if we can find one. Let's say x was 0. If I said y was 3, that would not be less than the x plus 1, right? So that would not be part of what we call our solution set. What if I said x was negative 5? Well, let's see. Or x is 0, y is negative 5. That negative 5 would be less than 0 plus 1. Great. If x is 14, any y value that's less than 15 would be in the solution set. So maybe 9. If x is negative 27, anything less than negative 27 plus 1 would be in the solution set. Not negative 26, though, because that's actually equal to, so we're not going to include that. So maybe negative, if x is negative 27, maybe negative 100. That's less than negative 26. If x is 1,000, y could be anything less than 1,001. Maybe 999. And again, there are infinitely many combinations here, right? Infinitely many points that could satisfy that inequality. So this is another thing. I don't want to just list the values. I want to give a graphical representation. So here's what we do. We're going to go to the graph. We're going to graph y equals x plus 1. We're going to think about that. So let's see, y equals x plus 1, y-intercept of 1, slope of 1, boom, boom. We know what this looks like. We've been doing this since December. We are so good at graphing things now. All right, there's our line. Y equals x plus 1. But what we want is all of the values that are less than, all the values where the y is less than that x plus 1. This is a piece of cake. All we're going to do is we're going to shade below that line. So our solution here, our answer is the graph itself. And the graph is this. Some of you will be really neat shaders. Some of you will be, like me, very sloppy shaders. I couldn't care less. I can't promise you what your Algebra 2 teacher will want you to shade like, and I can't promise you what anybody else will want you to shade like, but if you are messy, that's fine. I don't care. What that represents is that any point in, that's what we call the solution set, any point in that shaded region is part of the solution set. It means if we pick any number, like for example, let's pick this point, negative 1, negative 3, that should satisfy this inequality. The y is negative 3, that should be less than negative 1 plus 1, and it is. That point satisfies that inequality. 0, 0 should be in that solution set. Is 0 less than the x is 0 plus 1? Yes, it is. If I picked a point up here, like negative 2, 4, let's see, if the y value is 4, is that less than negative 2 plus 1? Well, no, it's not, so that point is not in our shaded region. So that's what we're going to do. We're going to graph, and we're going to color. Easy, right? Here's the exception. Here's the issue. If I pick a point that's on that line, like let's say I pick 1, 2, I'm asking myself for that point 1, 2, is the y value less than the x value plus 1? No, it's not. It's actually equal to, right? Any point on that line is not going to satisfy this inequality because it's not less than or equal to, it's just less than. So what, just like we had the open circle, closed circle with the other inequalities we did, we have the same kind of thing here. What we use to indicate that it's points not on the line are not included, points on the line are not included, is we're going to use a dotted line instead of a solid line, or sometimes students will call that a dashed line. So we do that, all right? So if it's just less than or just greater than, we're going to use a dotted line, okay? So like an open closed circle thing, no big deal. Here's another one, y greater than or equal to negative 1/2 x plus 2. So again, we're going to go to the graph. We're going to graph. There's 2. Slope is negative 1/2. Now this one is greater than or equal to. Every point on this line will be included, so we're going to use a solid line here. Now this one is greater than or equal to. Greater than or equal to, we're going to shade above that line. Don't think left or right, think above or below. So if I shade above the line, looks like this. I apologize to those of you who are so precise with your coloring. I was never a good colorer even as a little girl. I always envied the girls who could color well, but that was not me. So that's about it. So we graph and we shade. Sometimes the lines will be in standard form. Guess what we're going to do? We're going to put them in slope-intercept form, subtract that 2x, and subtract the 2x. We get y is less than negative 2x minus 3. Minus 3 up 2 over 1. This is a strictly less than, so I'm going to use a dotted line or a dashed line. And again, it's less than, so I'm shading lower than. Might want to go to that y-intercept and refer to all of the y's that are less than that point. Less than that would be underneath it. Again, don't think left-right, because that's going to change based on the whether the slope is positive or negative. Think above or below is what we're shading. One more, just a quick reminder, putting this in standard form, subtract that x, negative 3y less than or equal to negative x plus 6, and then I'm going to divide by that negative 3, that thing we talked about in the fall, that rule that will always be there with inequalities no matter where you are or what you're doing. If we divide by that negative, we need to flip that inequality around. So that would be a 1/3 x minus 2. Minus 2 up 1 over 3. Again, this is now a solid line because it's greater than or equal to. Greater than or equal to means I'm going to shade above. And that's that. Again, the idea here, and it goes forever, forever and ever and ever, the idea here is any point in that shaded region will satisfy that original inequality. Just a quick little graph for you. We got things going on here. Dotted line, solid line, shading above, shading below. If y is less than or y is greater than, you've got a dotted line. Less than or equal to, greater than or equal to, that's a solid line. Shading below is a y is less than or a y is less than or equal to. Shading above, y is greater than. My dog is scratching his neck. Can you hear that? Y is greater than or y is greater than or equal to. And that's it. Focus mostly on your tests for tomorrow. We'll cover these again in class, but that's kind of where we're headed. There's really not much more to it than that. So you've got a sneak preview of what's coming next week. All right, have a wonderful day. Bye, guys.